Hello friend, so glad you're here tonight. Get comfortable, pull the covers up, and let the day loosen its grip. There's nowhere else you need to be. Before we begin, a small request. Most of the people listening tonight aren't subscribed. If this channel has ever helped you drift off, take a moment to subscribe and tap the like button on tonight's video. Both are free, they take 2 seconds, and they help this channel more than you'd think. And you can always change your mind later. And if you feel like it, leave a comment telling me where in the world you're listening from and what time it is where you are. I love reading them. Tonight is a slow drift through the real story of solar system, one true thing at a time. There is nothing to do here and nothing to remember. Each one will pass like a slow cloud, some familiar, some quietly surprising, all of them real. If you fall asleep somewhere in the middle, that is exactly how this is meant to work. Settle in, let your breathing slow down, and we will begin. One more thing before we begin. I'm also a co-founder of a sleep app, built to be the most affordable one out there. No ads, ever. Just sounds and stories made to help you sleep. It may not be released yet as this video goes up, but if you're watching a little later, it might be out by now. Just search for it, it should be easy to find. It works on iPhone, Android, and everything in between. Downloading it is the best way to support this channel. The solar system is estimated to have formed approximately 4.6 billion years ago. This was a period when the cosmos was young, filled with vast clouds of gas and dust. Over millions of years, these materials slowly began to clump together due to gravity's gentle tug. As time passed, the spinning cloud flattened into a disk, giving birth to our solar system. The light from distant stars illuminated this process, providing a glimpse into the early days of our universe. Through meteorites and moon rocks, scientists have gathered evidence that supports this ancient timeline, offering insights into the origins of our celestial home. These ancient clouds were predominantly composed of hydrogen and helium, the basic building blocks of stars. As they collided and coalesced, they formed increasingly dense regions that would eventually give rise to the Sun at the solar system's center. The remaining materials, enriched with heavier elements, coalesced into planets, moons, and other celestial bodies. Analysis of these elements in meteorites has provided valuable clues about the composition and evolution of the early solar nebula. The leftover gas and dust from this process eventually formed comets, asteroids, and the Kuiper Belt objects. The heat and pressure inside these nascent planets caused differentiation, with heavier elements sinking to form cores. Scientists use spectroscopy to analyze the light from stars, seeking signs of similar planet-forming processes elsewhere in the galaxy. By studying the isotopic ratios in meteorites, researchers can trace the solar system's evolution back to its molecular cloud origins. The solar system is located in the Orion spiral arm of the Milky Way galaxy. This arm is a long, winding structure that stretches across the galaxy. It is filled with stars and their respective planets, all moving together through space. The spiral arms are thought to be formed by the gravitational pull of nearby galaxies, causing our own to stretch out into these distinctive shapes. Over time, scientists have observed and mapped the Milky Way, using telescopes and other instruments to understand its structure. By studying the light from distant stars, they can determine their distance and position within the galaxy. This information helps us place the solar system precisely in the Orion spiral arm. The motion of the solar system within this arm helps maintain a steady environment for life. The gravity of the galaxy's center pulls the arm inward while the rotation keeps it stretched out. By measuring the Doppler shift of starlight, astronomers can track the movement and speed of stars within the spiral arm. By analyzing the spectral lines from starlight, scientists can calculate how quickly the solar system is moving through space. This measurement reveals a consistent pattern that aligns with our understanding of spiral arm dynamics. The relative motion of the solar system within the Orion spiral arm shows a harmony between the gravitational forces and rotational momentum of the galaxy. Observing these motions over extended periods has refined our models of galactic evolution, providing deeper insights into the structure and behavior of the Milky Way. The Oort cloud is the solar system's outer boundary, reaching about 1 light-year from the Sun. This cloud of icy objects is a distant realm that defines where our solar system ends. Its existence was inferred by astronomers studying comets, as some travel from this faraway region. The cloud is spherical, surrounding the entire solar system like a shell. Light takes a year to traverse its vast distance, illustrating how far it stretches. This boundary is shaped by gravitational forces, keeping these icy bodies in their distant orbits. Our understanding of the Oort cloud comes from mathematical models and observations of long-period comets. The Oort cloud provides a protective layer around our solar system, shielding it from interstellar threats. Its formation is believed to be a result of the early solar system's dynamics, where icy materials were flung outward. Comets traveling towards the Sun are thought to originate from this cloud, providing evidence of its existence. The cloud's influence on our solar system extends far beyond what we can visually observe, shaping the trajectories of celestial bodies that venture inward. The Oort cloud's presence is inferred from comets that take millions of years to complete one orbit around the Sun. Its distant location ensures minimal gravitational influence from other celestial bodies, preserving its stability. The discovery of long-period comets with near-parabolic orbits provided crucial evidence supporting the existence of this cloud. Astronomers used telescopes and mathematical models to study these icy objects, further solidifying our understanding of the Oort cloud's dynamics. In 1977, two spacecraft named Voyager 1 and 2 were launched on a mission to explore the outer reaches of our solar system. This exploration included planets such as Jupiter, Saturn, Uranus, and Neptune, which are distant from Earth. The spacecraft journeyed through vast distances, propelled by the force of their launch. As they traveled, they sent back valuable information about these far-off worlds, helping scientists understand more about our solar system's composition. These missions were designed to continue beyond the known boundaries of our solar system and into interstellar space, marking a significant milestone in human exploration. These spacecraft carry messages from Earth, intended for any beings that might intercept them. They are now in interstellar space, where they continue to transmit data. The information gathered helps us understand what lies beyond our solar system's edge. This journey is ongoing, with the spacecraft sending back valuable insights about interstellar space. These spacecraft have now crossed the heliopause, the boundary where solar wind meets interstellar wind. They measure magnetic fields and cosmic rays in this unexplored region. Their journey is silent, with no human voice to guide them. The data they collect takes years to reach us, traveling at the speed of light. The signals from these distant probes take years to traverse the immense distance, each photon carrying a whisper of data across the void. This silent dialogue allows us to glimpse conditions far beyond our solar system's edge. By analyzing the magnetic fields and cosmic rays encountered, scientists gain insights into the nature of interstellar space. The enduring mission of Voyager 1 and 2 exemplifies human curiosity, extending its reach into the unexplored realms of the universe. In 1977, the Solar Energy Research Institute was established. This institute, now known as the National Renewable Energy Laboratory, played a significant role in advancing solar energy research. Over time, it has contributed to the growth of the US solar market. The Solar Energy Industries Association, formed to support this industry, has been instrumental in promoting the use of solar energy nationwide. This association advocates for policies that facilitate the integration of solar power into the grid. As a result, more homes and businesses are now able to generate their own electricity using solar panels. The advancements made by these institutions have led to innovations in solar technology, making it more efficient and accessible. As solar power becomes more affordable, it attracts a wider range of adopters. By reducing dependency on fossil fuels, solar energy helps mitigate environmental concerns. Research into solar technology continually uncovers new materials and methods for enhanced efficiency. These discoveries are then applied to improve the accessibility and effectiveness of residential and commercial solar systems. This progress allows for a more sustainable future, as fewer resources are needed to produce clean energy. The widespread adoption of solar power reduces greenhouse gas emissions, thereby slowing climate change. ongoing research and development continue to refine solar technology, ensuring that it remains at the forefront of renewable energy solutions. As a result, communities worldwide can benefit from the environmental and economic advantages of solar energy. The improvements in solar technology have allowed for a more seamless integration into existing infrastructure. This is achieved by making panels more lightweight and easier to install, reducing the impact on building structural integrity. Solar power systems are now designed with user-friendliness in mind, enabling homeowners and businesses to monitor their energy usage in real time. Through extensive research, it has been discovered that certain materials can enhance the absorption of sunlight, leading to higher efficiency rates for solar panels. By 2020, the US had installed over 97 gigawatts of solar PV capacity. This means that across various states and cities, numerous solar panels were put in place, generating clean energy for homes and businesses. The price for installing residential solar systems ranged from $250 to $4.07 per watt during this time. Over the years, the steady increase in solar capacity can be attributed to both technological advancements and government incentives encouraging renewable energy use. As of the end of 2022, the US has installed over 160 gigawatts of solar capacity, showing a consistent growth trend. Each watt of installed solar power contributes to reducing dependence on fossil fuels, promoting a cleaner environment. The data collected from these installations provides insight into the efficiency and reliability of solar energy systems in various regions. The continuous rise in solar capacity underscores the growing acceptance and integration of renewable energy sources. As more homes and businesses adopt solar technology, the collective impact on reducing carbon emissions becomes increasingly significant. Regular monitoring and analysis of these installations enable researchers to refine solar technologies for greater efficiency. The ongoing expansion of solar capacity signifies a gradual shift towards a sustainable energy future. Solar installations across the country have transformed cityscapes and landscapes, with panels visible on rooftops and in open fields. Each solar panel installed helps lower electricity bills for residents and businesses over time. This trend is driven by a combination of falling panel costs and increasing public awareness about climate change. Researchers studied the performance data from these installations to understand how different factors like weather patterns and shading affect solar energy production. The Department of Energy offers resources for homeowners to go solar. These resources include a detailed guide provided by the Department of Energy, helping homeowners understand how to harness solar energy for their homes. The Department of Energy has compiled this information to assist homeowners in making informed decisions about transitioning to solar power. This homeowner's guide covers various aspects of solar energy, from understanding how solar panels work to evaluating the financial benefits of going solar. By offering such comprehensive resources, the Department of Energy aims to make the process of adopting solar energy more accessible and straightforward for homeowners across the country. The guide is designed to be user-friendly, ensuring that even those with little prior knowledge can navigate the complexities of installing and utilizing solar systems effectively. This guide not only explains the technical aspects, but also provides real-life examples to illustrate the practical benefits of solar energy. By demystifying the process, the Department of Energy hopes to alleviate common fears and misconceptions that might deter homeowners from adopting solar power. The content is regularly updated based on feedback from users and advancements in solar technology. This ongoing refinement ensures that homeowners have access to the most current and reliable information available. Homeowners can find reassurance in knowing that the Department of Energy regularly reviews and updates its resources to reflect the latest advancements in solar technology. This continual effort ensures that the information provided remains accurate and relevant for those considering a transition to solar power. The department's commitment to keeping homeowners informed is rooted in a deep understanding of the evolving nature of renewable energy solutions. By maintaining open communication channels with industry experts and users, the Department of Energy stays attuned to emerging trends and addresses any concerns promptly. The Hubble Space Telescope was launched into orbit in April 1990, marking a significant milestone in our exploration of the cosmos. This powerful instrument has revolutionized our understanding of the solar system by capturing light from distant celestial bodies and translating it into data for scientists to analyze. The telescope's unique vantage point in space allows it to peer deeper into the universe than ground-based observatories, enabling astronomers to study galaxies, stars, and planets with unprecedented clarity. Its precise mirror system collects light that has traveled billions of years through space, providing insights into the formation and evolution of our solar system. The telescope's advanced technology includes various instruments that capture images across different wavelengths, revealing the intricate details and composition of celestial objects. Through its extensive observations and discoveries, Hubble continues to be an invaluable resource for astronomers and space enthusiasts alike. The telescope's location beyond Earth's atmosphere allows it to avoid distortions caused by air, ensuring clearer images. This ability to observe without interference has led to groundbreaking discoveries about the universe's composition and behavior. Astronomers study these detailed observations to uncover secrets of the cosmos, such as the age and chemical makeup of distant galaxies. The continuous stream of data from Hubble provides a rich resource for scientists, enabling them to refine their theories about the formation and evolution of the universe. Hubble's ability to observe in different wavelengths, such as visible light and infrared, provides a more complete understanding of celestial objects. The absence of Earth's atmospheric interference allows Hubble to capture images with greater accuracy and detail than ground-based telescopes. Astronomers use these images to study the physical properties of stars, galaxies, and nebulae, leading to new discoveries about their composition and behavior. By analyzing light from distant objects, scientists can determine their age, distance, and chemical composition, offering insights into the universe's past. The Wikipedia page for the solar system lists exactly 246 languages. This number reflects the wide reach of human interest in our celestial neighborhood. Each language brings a unique perspective, shaping how we understand and explore the solar system. The diversity of languages indicates that astronomy has been studied and appreciated across numerous cultures over time. This global fascination allows us to share discoveries and deepen our collective understanding of the cosmos. Languages help document observations, record theories, and communicate findings among astronomers worldwide. As a result, the solar system becomes more accessible to people from various backgrounds, fostering a shared sense of wonder and curiosity. This linguistic variety underscores the universal appeal of astronomy. Each language contributes distinct vocabulary and idioms, enriching our comprehension of celestial phenomena. The spread of these languages across continents attests to the global exchange of astronomical knowledge. Continuous translations facilitate the seamless flow of information, making space exploration a collective endeavor. The presence of diverse languages in solar system literature highlights the interconnected nature of human knowledge. This breadth of linguistic representation arose as communities worldwide engaged with astronomical observations. The accumulation of these records over time has illuminated the universality of celestial phenomena. As more individuals contribute to the study of our solar neighborhood, the collective understanding continues to expand. This rich tapestry of languages signifies a shared human experience. Observations and findings travel across borders, bridging cultural divides. Communities around the world have long looked to the skies, recording what they see in their native tongues. The evolution of our understanding is marked by these multilingual records. Stony Brook University's self-service system is named Solar. It serves the entire university, providing a centralized platform for students and staff to manage their academic and administrative tasks. This enterprise-wide system simplifies processes like course registration, financial aid applications, and transcript requests. By consolidating these services into one place, it enhances efficiency and accessibility. The name Solar is likely inspired by the solar system, suggesting a centralized point of control that guides various activities within its orbit. This naming convention is practical, as it helps users easily recall and navigate the platform. Over time, feedback from users has refined the system, ensuring that it meets their evolving needs. The design of Solar emphasizes user-friendliness, making complex tasks more straightforward to complete. Solar's design prioritizes clear layouts and intuitive menus, ensuring that even those less familiar with technology can use it effectively. Through regular updates, Solar adapts to user preferences and emerging technologies, integrating new features based on user feedback. By offering step-by-step guidance for complex tasks, the system minimizes errors and reduces the need for additional support. Continuous monitoring of user behavior helps identify pain points, leading to targeted improvements in functionality. Solar's adaptability ensures that users can rely on it for consistent support. The platform's iterative development process allows for gradual enhancements based on user experiences. This approach to design maintains Solar's relevance in the face of changing technological landscapes. By continually refining its features, Solar stays aligned with the needs of both students and staff. Solar's interface is designed with user comfort in mind, utilizing clear fonts and sufficient spacing to avoid visual strain. The system employs a color coding scheme that differentiates sections, making navigation intuitive for all users. Regular usability tests conducted with actual users help identify any potential barriers in the design. These insights are then incorporated into subsequent updates, ensuring that the platform remains accessible and efficient. The first solar cell was created by Bell Labs in 1954, achieving an efficiency of 6%. This breakthrough in converting sunlight into electricity marked a significant step forward. The process involves placing a semiconductor material on a surface, allowing it to absorb photons from the sun's light. These absorbed photons then release electrons, generating a small electrical current. Researchers at Bell Labs spent years experimenting with different materials and configurations to maximize this effect. The resulting 6% efficiency meant that the solar cell could convert a small portion of the sunlight it received into usable energy. This discovery laid the groundwork for further advancements in solar technology, paving the way for more efficient cells in the future. This initial efficiency was a result of the semiconductor material's properties and its ability to absorb specific wavelengths of light. By studying how different materials interacted with sunlight, researchers were able to understand the underlying principles that allowed for this conversion. They observed that certain materials release more electrons when exposed to light, leading to greater electrical output. This understanding provided a foundation for improving solar cell design and performance. This discovery meant that sunlight could now be harnessed to generate electricity, providing a renewable source of power. The ability to absorb light and release electrons is a fundamental property of semiconductors, making them crucial for solar energy conversion. By experimenting with various materials under controlled conditions, scientists were able to measure the efficiency of each setup, leading to deeper insights into photovoltaic principles. Over the past decade in the United States, the cost of solar has decreased by more than 70%. This reduction has made it easier for homes to adopt solar power. As of 2021, the country has an installed solar capacity of over 90 GW, capable of powering approximately 18 million homes. The average cost of installing a residential solar PV system in 2019 was around $2.96 per watt. This decline in costs is due to advancements in technology and increased production efficiency. Solar panels have become more affordable, encouraging widespread adoption. The decrease has also been facilitated by government incentives and the growing demand for renewable energy sources. As more homes switch to solar, the overall cost continues to drop, making it a viable option for many. Solar power has transitioned from a luxury to an accessible choice for many households. This shift reflects the continuous refinement of solar technology and manufacturing processes. The falling costs signal a growing industry, with more companies entering the market to meet rising demand. As more homes adopt solar, further efficiencies are expected, reinforcing the trend of decreasing prices. The decrease in solar costs has been steadily documented through annual reports and industry analyses. This trend shows that as technology advances, it becomes less expensive to produce and install solar panels. The lower cost makes solar power more accessible to a wider range of consumers. Consequently, the increase in demand for solar energy drives further technological improvements, creating a self-reinforcing cycle. The affordability of solar panels has opened doors for families who previously could not consider such an upgrade. By making renewable energy more attainable, these lower costs have brought about a shift in consumer behavior. This trend was uncovered through detailed studies tracking price changes and installation growth over the years. The declining prices signal that the solar industry is maturing, with efficiencies being passed on to end users. The U.S. Department of Energy supports research and development efforts to advance solar energy technologies. This support encompasses various studies, from improving solar panel efficiency to developing new materials that can better capture sunlight. These technologies are crucial for a sustainable future, reducing our dependence on fossil fuels. Over time, advancements in solar energy have shown promise through field tests and laboratory experiments, demonstrating the potential of clean energy solutions. The department's commitment to solar research reflects a broader global effort to transition towards renewable energy sources, ensuring a greener tomorrow. By investing in innovative methods, scientists aim to enhance the way sunlight is converted into usable power, making it more accessible and cost-effective for households and industries alike. These advancements aim to optimize solar cells for greater electricity output and longer lifespans. Researchers explore ways to minimize energy loss during conversion, maximizing the sun's power potential. Laboratory findings indicate that enhanced materials can withstand harsh conditions, ensuring consistent performance in various environments. Additionally, field data suggests that innovative designs can lower production costs, making solar technology more affordable for widespread adoption. The research includes experiments with materials like perovskite and organic semiconductors, which show potential for high efficiency at lower costs. Laboratory experiments also involve simulating different weather conditions to observe the stability of solar panels over time. Scientists are studying how to enhance the durability of solar cells by applying protective coatings that prevent degradation from sunlight exposure. Field tests help validate these improvements by monitoring long-term performance in real-world settings. The first solar-powered aircraft, Solar Impulse 2, completed a round-the-world flight in 2016. This feat was accomplished using the sun's energy to power the plane. The journey spanned numerous days and nights, demonstrating the aircraft's ability to store energy during daylight hours for use at night. Surfaces of the plane were covered with solar cells, converting sunlight into electrical energy that propelled it through the skies. This achievement showcased the potential of solar technology in long-distance travel. It took years of research and development to create an aircraft capable of such a journey. The successful flight validated the efficiency of renewable energy sources for powering transportation. This aircraft, with its lightweight design and expansive wingspan, was able to harness solar energy efficiently. The ability to fly continuously, day and night, without refueling, demonstrated the feasibility of sustainable aviation. Solar Impulse 2's journey highlighted the possibility of integrating renewable energy into modern transportation systems. This achievement underscored the practicality of using clean energy for long-distance travel. This aircraft, equipped with innovative solar technology, challenged traditional aviation methods. Its lightweight structure and solar cells enabled it to collect and store energy from the sun. This design allowed the plane to fly without conventional fuel, relying solely on sunlight. The successful completion of this journey marked a significant step towards sustainable aviation practices. The aircraft's ability to fly continuously without conventional fuel signifies a shift in aviation technology. By harnessing solar energy, the plane challenges the dependence on fossil fuels for long-distance travel. This advancement is made possible through years of research and technological innovation. As renewable energy sources become more integrated into transportation systems, the future of sustainable aviation looks promising. The distance of Mercury from the Sun is approximately 0.39 astronomical units, AU. This means that Mercury orbits about 3 times closer to the Sun than Earth does. The AU is a unit of length defined as the average distance from Earth to the Sun, so 2.39 AU is just over 1/3 of that distance. The closeness of Mercury to the Sun results in it experiencing more intense sunlight and heat. This proximity was first calculated by observing Mercury's orbit and comparing its position relative to other planets and the Sun. It takes light about 3 minutes and 7 seconds to travel from Mercury to Earth, illustrating how close it is to our star. This close orbit also affects Mercury's surface temperature, which can range from 100K at night to 700K during the day. The intense sunlight causes Mercury's surface to weather and erode over time. This information about Mercury's proximity to the Sun is crucial for understanding its unique environment and geological features. It has been observed that this closeness also influences Mercury's tidal lock, causing it to rotate on its axis at a slower rate than other planets. The extreme temperatures cause Mercury's surface to expand and contract significantly. This constant cycle alters the planet's landscape over time, creating vast cracks and ridges. Observations of Mercury from different vantage points on Earth have helped scientists study this dynamic process. The data collected from these observations has enabled researchers to create detailed maps of Mercury's surface, revealing its complex geology. The distance of Earth from the Sun is approximately 1.0 AU, a measure defined by the average distance between our planet and its star. This single unit of measurement helps us understand that Earth lies at the starting point of our solar system, with Jupiter, the largest planet, being over 5 times farther away at about 520 AU. Saturn, the next planet outward, orbits at roughly 958 AU, giving us a sense of how much more distant these gas giants are compared to Earth. This knowledge comes from centuries of astronomical observations and calculations, allowing us to map the celestial bodies in our solar neighborhood with remarkable accuracy. These measurements allow us to plot each planet's orbital path, revealing how far they travel from the Sun. By studying the light from distant stars, we can infer their distance using similar methods. This scale helps us grasp the relative sizes of planetary orbits within our solar system. These units also help us compare the sizes of different planetary systems. The orbits of these distant worlds can be measured in similar ways using light and time. This knowledge comes from understanding how light travels through space. By observing stars that are near each other in the sky, we can calculate their relative distances. Light takes about 8 minutes and 20 seconds to travel from the Sun to Earth, providing a consistent benchmark for distance. The further a planet is from the Sun, the longer it takes light to reach us, allowing astronomers to calculate its orbital distance. By comparing the time it takes for light to arrive from different stars, scientists can determine their relative positions in space. This method relies on precise measurements of light's journey through the cosmos. The order of the 8 official solar system planets from the Sun, starting closest and moving outward, is Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. This sequence is based on the proximity of each planet to our star, the Sun. The first 4 planets are known as the inner planets due to their relatively close distance to the Sun. Moving further out, we find the gas giants, starting with Jupiter, which is more than 300 times the mass of Earth. These planets are often referred to as the outer planets because they lie beyond the orbit of the inner planets. This arrangement was first observed through telescopes and later confirmed by spacecraft explorations. The vast distances between these planets create a sense of scale that is difficult to comprehend without such observations. The space between each planet grows larger as you move away from the Sun, with Neptune's orbit being more than 30 times wider than Earth's. This arrangement is the result of the Sun's gravitational pull, which decreases with distance. Observations and calculations have allowed us to understand this layout, revealing the vast empty spaces that separate our planetary neighbours. The space between each planet is not merely empty, but filled with smaller celestial bodies like asteroids and comets. This spacing allows planets to orbit in a stable manner without colliding. By observing the movement of these planets over time, astronomers have mapped their orbits. These paths are elliptical, following a predictable pattern around the Sun. These stable orbits are maintained by the balance between the Sun's gravitational force and each planet's momentum. Astronomical observations over centuries have refined our understanding of these paths. The trajectories are influenced by the presence of other celestial bodies within each orbit, creating slight variations in the planetary movements. Jupiter's moon, Io, is indeed the most volcanically active object in our solar system, boasting over 400 active volcanoes. These volcanoes spew molten sulfur and lava, painting Io with vibrant colors. The heat from these eruptions is so intense that it can be detected from millions of miles away by spacecraft sensors. This high level of activity is due to the gravitational forces exerted by Jupiter and its other moons. As Io orbits, it is pulled and stretched, generating enough heat to power the volcanic eruptions. Over time, observations from space probes like Galileo have revealed these details about Io's surface. The lava flows and plumes are a constant reminder of the dynamic processes shaping our solar system. The heat from these tidal forces creates a network of volcanic vents across Io's surface, with some eruptions reaching heights of hundreds of kilometers. The continual stretching and compressing of the moon's interior releases enough energy to sustain these powerful eruptions. Observations of Io's plumes using infrared spectrometers have identified various chemicals ejected during these events, such as sulfur dioxide and sodium chloride. These compounds contribute to the complex composition of Io's atmosphere, further illustrating the intricate relationship between its geological activity and Jupiter's gravitational influence. The heat generated by these tidal forces also shapes Io's surface, creating vast lava lakes and rivers that flow across its frozen crust. The constant churning of the moon's interior ensures that fresh molten material is regularly brought to the surface. This ongoing volcanic activity has been observed through infrared imaging, allowing scientists to study the chemical composition of Io's plumes without needing to land on the moon itself. The gravitational forces at play create a dynamic landscape where new eruptions constantly reshape and rejuvenate the surface, providing valuable insights into the geological processes that drive volcanic activity across the solar system. The economy of the solar system relies largely on extracting resources and welcoming tourists, with Mars and the Moon being prime spots for future homes. The red, dusty surface of Mars offers a promising environment for mining essential minerals, while the grey lunar landscape holds potential for establishing bases. Tourism in space is growing, drawing adventurers eager to explore celestial bodies beyond Earth. Resource extraction and tourism are interconnected, as new habitats fuel demand for supplies and services. The Moon's proximity to Earth makes it a logistical advantage for initial exploration and setup of lunar outposts. Mars, although farther away, presents unique opportunities with its day-night cycle similar to Earth's. Astronomers have used telescopes to observe the surfaces of these celestial bodies over time, revealing their potential. This information is invaluable for planning future missions and habitation efforts. As technology advances, more detailed studies will continue to shape our understanding of these distant worlds. The red planet's water ice deposits hint at past habitable conditions, making it an ideal candidate for future life support systems. The Moon's stable temperature ranges throughout its day-night cycle are favorable for technological equipment operation. Observations from spacecraft have provided detailed maps of Martian and lunar surfaces, aiding in mission planning. Over time, these celestial bodies have been found to be more accessible than previously thought. The accessibility of these celestial bodies has been determined through thorough analysis of their atmospheres and surfaces. The presence of water ice on Mars indicates a feasible source for life support systems. Detailed mapping from orbiting spacecraft has enabled precise identification of resource-rich areas. Further exploration will reveal more about the practicality of habitation in these distant environments. The solar system is composed of the Sun and all objects orbiting around it. At its center lies the Sun, a star that provides light and heat to everything within its sphere of influence. This includes planets, large bodies like Earth and Jupiter, each with their own distinct surfaces and atmospheres. It also encompasses moons, smaller celestial bodies that circle the planets, adding to their complex orbital dynamics. Dwarf planets, such as Pluto, add further diversity to this system, exhibiting unique characteristics despite their size. Asteroids and comets, often referred to as minor planets, follow their own paths through the solar system, sometimes intersecting with those of larger bodies. The vast number of objects in the solar system is a result of centuries of astronomical observations and discoveries, continually expanding our understanding of this intricate cosmic neighborhood. Each object within this system plays a role in shaping its environment, from the sun's light influencing plant growth on Earth to Jupiter's gravity protecting the inner planets. The solar system's formation is traced back to the collapse of a giant molecular cloud, leading to the birth of our star and the protoplanetary disk that birthed the planets. Through telescopic observations and space exploration missions, we have gathered detailed images and data, enhancing our grasp of this interconnected realm. This interplay of celestial bodies and their interactions creates a dynamic system. Each object's trajectory is governed by gravity, defining its path through space. Observations from Earth and space-based telescopes reveal these movements over time. The collected data provides insights into the system's stability and evolution. The Sun is the largest object in our solar system, making up over 99% of its mass. This immense body, a star that fuels life on Earth with its energy, dominates the celestial neighborhood. Its gravity binds together the planets and other bodies orbiting it. The sheer scale of this giant can be grasped when we consider that more than 99.86% of the mass in our solar system is contained within it alone. Scientists have calculated this precise figure through years of observation and measurement, confirming the Sun's central role. Its immense gravity not only keeps planets in their orbits, but also shapes the trajectories of comets and asteroids. Despite its distance, the Sun's influence permeates every corner of our solar system, from the scorching surface of Mercury to the icy rings of Saturn. This knowledge is more than just an astronomical fact. It underscores the profound interconnectedness of our cosmic home. The Sun's gravity also affects the shape and orientation of planets, causing some to tilt and others to rotate more rapidly. This gravitational pull is so strong that it can even slightly warp the fabric of space-time. Over time, careful measurements and mathematical models have refined our understanding of this immense force. The Sun's influence is further evident in the tidal forces it exerts on Earth, causing the oceans to rise and fall. The Sun's gravity even influences the paths of spacecraft sent into the solar system, requiring precise calculations to navigate their orbits. This understanding is based on observations of planetary motions and the behavior of celestial bodies under gravitational forces. The study of these interactions has led to advancements in predictive models for astronomical phenomena. Observing the effects of the Sun's gravity helps us understand the dynamics of our solar system, ensuring accurate forecasts for future events. In the 1970s, the cost of PV modules was around $100 per watt. At that time, solar power was still an expensive investment, making it less accessible to many. Yet, over the decades, significant advancements in technology and manufacturing have led to a substantial reduction in costs. By 2020, the cost had dropped significantly, reaching approximately just a $50 per watt. This dramatic decrease is largely due to improvements in panel efficiency and economies of scale. The solar industry has seen growth and innovation, making solar energy more affordable and widespread. Today, the cost per watt stands at about 0.36, a remarkable achievement from the earlier figures. This shift reflects not only technological progress, but also increased demand and support for renewable energy solutions. As we continue to explore and harness the power of the sun, these advancements pave the way for a more sustainable future. This cost reduction has made solar power accessible to a broader range of consumers and businesses. The improvements in technology have enabled more efficient use of sunlight, while larger production scales have driven down the manufacturing costs. As a result, more people are choosing to invest in solar energy solutions. These advancements have been documented through various studies and reports, highlighting the steady progress in the field. This decline in costs has made solar power a viable option for many more homes and businesses. The increased efficiency of panels means that less space is needed to generate the same amount of electricity. researchers have found that ongoing technological refinements will continue to lower the price per watt. The growth in the solar industry has been driven by these cost reductions, making renewable energy more attractive. The Avanpar Solar Electric Generating System is one of the largest CSP plants in the world, standing tall in California's Mojave Desert. It harnesses sunlight with thousands of mirrors, carefully arranged to reflect and concentrate the rays onto boilers atop 3 solar power towers. These mirrors work together, a precise arrangement designed to maximize efficiency. The facility is known for its ability to generate 392 megawatts of electricity, enough to power many homes during peak sunlight hours. This impressive capability comes from the plant's concentrating solar power system, which converts the sun's energy into heat and then into electrical power. The mirrors are constantly adjusted throughout the day to ensure that sunlight is always focused onto the boilers, maintaining a steady stream of electricity. As one of the world's leading CSP plants, it plays a significant role in renewable energy production, demonstrating the potential of solar technology on a large scale. The facility's mirrors are controlled by sophisticated tracking systems, ensuring accurate sunlight reflection. This design allows for continuous energy production throughout the day. The plant's efficiency is monitored and optimized through advanced software. The use of concentrated solar power showcases a viable alternative to traditional fossil fuel-based electricity generation. The facility's mirrors, each precisely calibrated, work in harmony to direct sunlight accurately. This intricate design allows for continuous energy production throughout the day. The plant's efficiency is monitored and optimized through advanced software systems. By harnessing concentrated solar power, it provides a steady stream of electricity during peak sunlight hours. Solar energy is radiation from the sun that is capable of producing heat, causing chemical reactions, or generating electricity. This radiant energy originates from nuclear reactions deep within the sun's core. When it reaches Earth, solar energy warms our planet, driving weather patterns and influencing climate. The light emitted by the sun also facilitates photosynthesis in plants, enabling them to grow and produce oxygen. Over time, humans have harnessed this energy using various technologies. Solar panels, for example, convert sunlight into electricity that powers homes and businesses. This natural resource is a vital component of renewable energy efforts worldwide. This energy is crucial for maintaining life on Earth, as it supports ecosystems and food chains. The mechanisms behind solar energy have been observed and measured using tools like spectrometers and telescopes. The sun's core releases this energy through a process called fusion, which combines hydrogen atoms into helium. This process occurs in the sun's interior, releasing heat and light that eventually reach our planet. The sun's light takes approximately 8 minutes to travel from its surface to Earth. Photosynthesis converts this sunlight into chemical energy, stored in plants for later use. Scientists observe the sun's activity using specialized instruments aboard spacecraft and satellites. The continuous flow of solar energy supports all life forms on our planet. Solar energy is a consistent, reliable source of power that fuels all living organisms. This radiant energy heats the Earth's surface and oceans, creating currents that shape our climate. Over time, humans have developed methods to trap and convert this energy into usable forms. The study of solar energy has advanced with the development of scientific tools that measure its intensity and properties. Solar is the fastest growing energy source in the world, adding 270 terawatt-hours of new electricity generation in 2022. This growth represents a significant increase in clean power, with sunlight harnessed through photovoltaic cells. The sun's rays, traveling at the speed of light, are converted into electrical energy. Each panel on a rooftop or in a field is a tiny piece of this global puzzle, contributing to the total. In 2022 alone, these panels added enough electricity to power countless homes and businesses. The exact measurement, 270 terawatt-hours, underscores the scale of this growth. This data comes from meticulous tracking by energy researchers worldwide, who compile reports on the state of solar power each year. Solar power's growth indicates a global shift towards sustainable energy. This increase is driven by advances in technology and policy support. Accurate measurements are gathered through satellite imagery and ground-based sensors, providing real-time data on solar panel output. These findings are crucial for planning future energy infrastructure. This growth signifies a move away from fossil fuels, reducing reliance on finite resources. The ability to capture sunlight efficiently is due to improved panel designs and lower costs of production. By analyzing both sunlight absorption rates and conversion efficiency, researchers can predict future solar power potential. These findings highlight the feasibility of further expansion in solar energy adoption. This surge in solar power is driven by technological improvements and reduced manufacturing costs. It reflects a global trend towards cleaner energy sources. The data collected from satellites and sensors allows for precise monitoring of solar panel performance. This information guides the development of future renewable energy projects. 270 terawatt-hours is enough to power a mid-sized state like North Carolina or Michigan. This amount of energy harnessed from the sun in 2022 added new electricity capable of sustaining the needs of everyday life for those regions. The sun's rays, when converted into usable power, can illuminate homes, run appliances, and keep communities thriving. Solar panels, spread across vast fields or rooftops, capture photons that have traveled 93 million miles from the star at the center of our solar system. These photovoltaic cells convert light energy into electricity, a process that has become increasingly efficient over time. As more solar farms come online, they contribute to the grid's capacity, ensuring reliable power for residential and commercial use. The ability to track and quantify this energy production allows scientists and engineers to understand the impact of renewable resources on our infrastructure. This data helps in planning future projects, as well as educating the public about the viability of solar power. This transformation of sunlight into electricity helps reduce our reliance on fossil fuels, contributing to a cleaner environment. By monitoring energy output from solar farms, we can analyze trends and optimize their performance. The conversion process involves semiconductors that absorb photons, creating an electrical charge. Data from these systems informs us about the efficiency of different solar technologies. These solar panels, when optimally oriented and cleaned regularly, can capture sunlight more effectively. The absorbed photons excite electrons in the semiconductor material, initiating a flow of electric current. This generated electricity can be sent directly to local power grids or stored for later use. Ongoing research aims to enhance the solar cells' efficiency and lifespan, furthering their potential impact on sustainable energy. Did you know? The sun's energy can power small, prosperous nations like Denmark or Ireland. It radiates a constant stream of light and heat, illuminating our days and warming our world. This solar energy is collected and converted into electricity by photovoltaic panels, providing clean power for homes and businesses. In a single hour, the sun delivers more energy than the entire human population uses in a year. By tapping into this abundant resource, we can meet our daily needs without relying on finite fossil fuels. Astronomers measure solar output using specialized instruments called radiometers, tracking changes over time to understand its influence on climate and weather patterns. This unending supply of renewable energy offers a promising future for sustainable living. Solar power is accessible and harnessed using photovoltaic cells, which absorb sunlight to create electricity. This clean energy source does not emit greenhouse gases, making it a responsible choice for our planet. By studying the sun's behavior through observations, scientists have gained insights into its predictable nature. The consistent output of solar energy allows us to plan and rely on its power generation. As the sun's rays hit Earth, photovoltaic cells convert this light into usable electricity. This process takes place without burning any fuel or producing waste. The continuous stream of sunlight ensures a steady supply of power throughout the day. By observing solar radiation, scientists have determined that its intensity and duration make it ideal for generating reliable energy. The sun's consistent energy output enables stable power generation, providing a predictable source for daily electricity needs. This reliable power flow is due to the Sun's uniform temperature distribution across its surface, creating a steady stream of light and heat. Observations from spacecraft have confirmed this stability over extended periods. As solar radiation reaches Earth, it provides a constant supply of energy that can be harnessed without interruption. Our solar system contains 8 official planets that orbit counterclockwise around the Sun. The orbits form a broad, curving path through space, with each planet following its own trajectory. This motion is governed by gravity, which pulls each planet in a consistent direction. Astronomers observe this pattern from our vantage point on Earth. The counterclockwise movement is determined by the perspective of an observer looking down upon the solar system from above its north pole. Over time, scientists have mapped these paths, creating detailed charts that trace each planet's journey. Each planet's path, known as an orbit, is an ellipse rather than a perfect circle. The gravity of the Sun keeps these orbits consistent over thousands of years. This understanding was first confirmed through observations made with early telescopes and refined with modern spacecraft data. These elliptical orbits vary in shape, with some planets traveling closer to the Sun and others maintaining a greater distance. This variation is due to the differing strengths of gravitational pull each planet experiences. Observations from different angles reveal the three-dimensional nature of these paths, further illustrating their complex dynamics. By studying the slight variations in a planet's speed throughout its orbit, scientists gain insights into the subtle influences of other celestial bodies within our solar system. The subtle gravitational tugs from neighboring planets cause the paths to shift slightly over time, creating intricate patterns within the orbits. This delicate interplay is recorded by precise measurements from orbiting satellites and ground-based telescopes. The data collected provides a detailed map of each planet's journey through space. By analyzing these movements, scientists can predict future positions and understand the solar system's evolving dynamics. In 2006, the International Astronomical Union reclassified Pluto as a dwarf planet, reducing the number of recognized planets in our solar system to 8. This change was prompted by new discoveries that led scientists to redefine what it means to be a full-fledged planet. For many years, Pluto had been considered the 9th planet, but its size and orbit were found to be different from the other known planets. As more objects like Pluto were discovered beyond Neptune's orbit in the Kuiper Belt, astronomers realized that Pluto should not hold the same status as larger bodies with clearer orbits. Thus, they created a new category called dwarf planets, to which Pluto was demoted. This decision has since sparked debates among scientists and enthusiasts alike about what truly constitutes a planet. This classification was based on 3 specific criteria. Firstly, a planet must orbit around the Sun, not another object. Secondly, it needs to have enough mass to be rounded by its own gravity. Lastly, it should clear its orbit of other objects, meaning no other large body should share its path. Pluto met the first 2 criteria, but failed the third, as it shares its orbit with numerous other Kuiper Belt objects. Additionally, observations and measurements from spacecraft like New Horizons provided detailed insights into Pluto's surface and atmosphere, further reinforcing the decision to reclassify it. This reclassification allows for a more precise categorization of celestial bodies. The definition of a planet is not arbitrary, it's based on observable characteristics. Through continued exploration, scientists gather more data to refine these classifications. As of 2021, solar power provided approximately 4% of the total electricity generated in the United States. This means that for every 100 units of electricity produced, about 4 came from the sun's energy. Solar panels convert sunlight into electrical power by absorbing photons and exciting electrons. The energy generated depends on the panel's efficiency and the amount of sunlight it receives. Experts track these figures using data collected from utility companies and government agencies. Over time, the percentage has been increasing as more solar farms are built and homeowners install panels on their roofs. As more communities embrace solar technology, this percentage is expected to rise. The data shows a steady increase in installed capacity year after year. Each panel contributes to this growing total, whether on rooftops or sprawling farms. This trend reflects our collective effort to harness clean, renewable energy. These panels capture sunlight during daylight hours, generating usable electricity. The process is ongoing as long as the sun shines and the panels are clean. Scientists analyze satellite imagery to monitor solar installations across wide areas. This information helps predict future energy needs and plan for further expansion. Solar panels on homes and businesses are visible across neighborhoods and cities, adding to the cumulative power generation. When sunlight is absorbed by these panels, electrons within them gain energy and create an electrical current. The collected data from satellites reveals a continuous growth in solar installations over large geographical areas. This data aids in calculating the potential future output of solar-generated electricity. All the planets move in the same anti-clockwise direction around the Sun, a pattern established by our solar system's formation. Picture 8 worlds orbiting together, each tracing its own path yet bound by gravity to this shared rhythm. This synchrony is the result of their common birthplace, a swirling cloud of gas and dust that coalesced into the Sun and planets some 4.6 billion years ago. Astronomers observe these movements over long periods, tracking celestial bodies with powerful telescopes to confirm their paths. The light from distant stars, altered by the planet's orbits, provides another clue, offering subtle changes that reveal their motion. This harmony of movement is a fundamental characteristic of our solar family, a silent ballet played out against the infinite canvas of space. This synchronized motion is governed by the gravitational pull of the Sun, ensuring that all planets move in a coherent manner. The planets' shared history and proximity to each other also contribute to this unison. Over time, observations from different points on Earth have confirmed this consistent direction. Astronomers use precise calculations to predict the future paths of these celestial bodies, further validating their coordinated movement. This alignment ensures a smooth trajectory, preventing collisions and maintaining stability within the system. Each planet's orbit is shaped by the Sun's mass, with their speeds decreasing as distance from the Sun increases. Careful study of the planet's positions over decades reveals this persistent motion, affirming its continual presence. This coordinated movement is what allows planets to maintain their respective positions in relation to one another, forming a stable system. The consistent anti-clockwise direction is due to the angular momentum inherited from the original cloud of gas and dust. Observing this motion has been possible through careful analysis of planetary positions recorded over many centuries. By volume, you could fit every other planet inside Jupiter. This is because Jupiter is by far the largest planet in our solar system, with a diameter that stretches about 139,822 kilometers across its surface. Located far from the Sun in the outer reaches of the solar system, Jupiter's formation was uniquely influenced by the leftover materials from the Sun's birth. This distant location allowed Jupiter to grow exponentially larger than its neighboring planets. Scientists have come to understand this through extensive study and comparison of the planets, revealing the true magnitude of Jupiter within our solar system. Jupiter's size is not merely a matter of volume, but also mass, as it comprises over 2.5 times the mass of all other planets combined. This disparity in size points to Jupiter's distinct formation process, far removed from the Sun's intense heat that limited the growth of inner planets. Studies of meteorites, which are remnants of the early solar system, have provided insights into Jupiter's composition and confirmed its rapid accretion. This immense size has significant implications for Jupiter's gravitational influence on its moons and the solar system at large. The planet's vast interior is composed mainly of hydrogen and helium, with traces of other gases. This composition was deduced from studying the gas giants and their similarities to Jupiter. Understanding the formation process has furthered our knowledge of how gas giants evolve in distant orbits. Jupiter's immense size is a result of its unique formation process, which occurred in the cooler outer regions of the solar system. This allowed Jupiter to accumulate more material over time compared to the inner planets. Observations and data from space probes have given us detailed insights into Jupiter's structure and composition. The rapid accretion of materials during its formation is evident in the planet's large size and high concentration of hydrogen and helium. Jupiter is composed mainly of hydrogen and helium, which make up over 90% of its mass. This massive planet, the largest in our solar system, has a diameter of about 140,000 kilometers. Its composition was first determined by examining light spectra from the planet's surface. Hydrogen is the most abundant element in the universe, making it no surprise that Jupiter shares this commonality. The gas giant's proximity to the Sun has allowed scientists to study its atmosphere extensively. Over time, these observations have revealed the true nature of Jupiter's composition. Despite its distance from us, Jupiter's size makes it an easy target for detailed analysis. Its vast size and relatively close orbit make it a prime candidate for continuous observation and research. The light from Jupiter's surface is captured and analysed using spectroscopy, revealing the presence of hydrogen and helium. The absorption lines in this spectrum match those produced by these elements under laboratory conditions. This method allows scientists to identify the composition of distant planets without physical samples. Understanding the dominant gases on Jupiter helps explain its colourful bands and storms, such as the Great Red Spot. The absorption lines in Jupiter's spectrum also indicate the presence of methane, ammonia, and water vapour, albeit in smaller quantities. These gases contribute to Jupiter's distinctive colours and banded structure. Scientists have used data from spacecraft flybys to refine their understanding of Jupiter's atmosphere over time. The observations continue to provide insights into the planet's dynamic weather patterns. The study of Jupiter's light spectra has also revealed trace amounts of other elements, providing a more complete picture of its atmospheric composition. The spectral analysis techniques used on Jupiter have since been applied to other gas giants in our solar system, expanding our knowledge of their compositions as well. Over time, advancements in telescope technology have allowed for even more precise measurements of Jupiter's light spectra, enhancing the accuracy of its atmospheric composition data. If visible, Jupiter's magnetic field would shine as one of the brightest objects in the night sky. This is due to the intense electrical currents that flow within it, creating a glow known as auroras. These auroras are similar to those seen on Earth, but much larger and more energetic. The immense size of Jupiter's magnetic field also contributes to its brightness, stretching out far beyond the planet itself. This field is so strong that it can even deflect high-energy particles from the Sun. Scientists have known about this since the 1950s, when they first detected radio emissions from the planet. These signals are a result of the magnetic field interacting with Jupiter's moons, particularly Io, which has its own strong magnetic field. Jupiter's magnetic field not only illuminates auroras but also protects the planet from solar winds. The field is shaped by Jupiter's rapid rotation and the complex dynamics of its interior. Measurements from spacecraft have revealed the field's intricate structure, providing valuable insights into Jupiter's core. Jupiter's magnetic field is not merely an astronomical curiosity, it plays a vital role in shaping the planet's environment. This protective barrier allows Jupiter to retain its gaseous atmosphere despite the Sun's intense radiation. The detection of radio emissions from Jupiter was made possible by advances in radio astronomy, enabling scientists to map out the invisible magnetic field. The magnetic field's bright glow is a direct consequence of the charged particles it traps and accelerates. This field acts as an invisible shield, repelling and deflecting incoming particles from the Sun. The precise nature of this interaction has been studied through detailed simulations and observations from spacecraft orbiting Jupiter. The data gathered reveals the magnetic field's dynamic behavior and its continuous influence on the planet's surroundings. Voyager 1 crossed the heliopause on August 25, 2012. This boundary marks where the solar wind's influence ceases to exist. The solar wind is a stream of charged particles that continually flows outward from the Sun. When Voyager 1 reached this point, it found no trace of these particles. Scientists determined its location through careful analysis of the spacecraft's data. They measured changes in cosmic ray levels and magnetic field strength to pinpoint this crucial threshold. This event marked a significant milestone for human exploration. It signified that Voyager 1 had entered interstellar space, leaving behind our solar system's protective bubble. The The spacecraft then began to detect particles from other stars, confirming its transition into interstellar space. This boundary is crucial because it indicates where our sun's protective influence ends and the cosmos begins. By studying this region, scientists aim to understand how stars like our sun affect their surroundings. The data collected by Voyager 1 continues to provide insights into this complex border. The heliopause acts as a protective barrier, shielding our solar system from harmful interstellar radiation. This boundary is not solid, but more like an invisible membrane shaped by the constant push and pull of the solar wind against the cosmic rays outside. Voyager 1's instruments detected this subtle shift by measuring slight changes in the magnetic field and particle density. The transition was gradual, with no abrupt signpost marking the boundary. Scientists had to meticulously analyze data over time to confirm its crossing. The solar wind's diminishing presence allowed Voyager 1 to encounter cosmic rays from distant stars, confirming its journey beyond our sun's dominion. This subtle shift in the space environment provided scientists with tangible evidence of the heliopause's location. The gradual change in magnetic field strength and particle density indicated a delicate balance between solar wind and interstellar medium. By analyzing these nuanced measurements, researchers could pinpoint Voyager 1's precise entry into the vast interstellar space. And that is where we will leave Solar System for tonight. The facts will still be true tomorrow, and this video will still be here whenever you need it. Sleep well,